Yeah, but I'm not blowing.
Chemistry.
It's about the introduction for Feng Shui series. We have already gone through that yesterday.
She wants to see our introduction.
Today?
Yeah, and the things I haven't started.
Today?
You feel upset.
Come on, dudes.
Oh my god, are you serious?
What?
She sent us an email yesterday. Even in the class, she said,
Jerry!
She wants to be our...
Monica! Jerry, it's simple. Just go to the class.
we
I
don't
was
have
dressed.
Yeah, good luck with that. Right. Decay. Got that? Yeah. Okay. So let's start. So this is the last section, which is atoms. Some of it will be familiar because you studied atoms in chemistry. So you know, a lot of it will be new, but not all of it will be new. So radioactive decay. Does anybody know what that is? I mean, you might have heard on TV or yeah. What is it exactly? Does anyone know?
Is it like disappear gradually?
Yeah, something's disappearing gradually. And what are we saying about energy?
Decrease.
The energy decreases, yeah. And it's something harmful.
Radioactive.
Yeah, so radioactive decay, also known as nuclear decay or radioactivity, is the process by which a nucleus of an unstable atom loses energy by ionizing radiation. And the types of radiation are... Does anyone know the types of radiation?
Yeah.
What are they?
UV.
No, that's for electromagnetic.
Alpha.
Alpha, beta, gamma.
Alpha, beta, and gamma.
Gamma.
Yeah, just like the Hulk. Are you eating a plain piece of white bread?
Yeah, I just need something else. I know.
What is it?
I don't have time for breakfast. I just grab it.
No time to even put a bit of butter on it?
I mean, I do, but I want to come earlier.
Could have, you know, waken up earlier. Okay, got that? Not yet, okay. Yeah? Continue? Jerry? No, I can wait a minute. What word are you on? Fine, the types are alphabetic gamma, that's fine. Yeah. Where are you, Chu?
Alpha, beta, gamma.
Good, okay.
Finish.
Oh, good, okay. Okay, Jerry.
What? No.
Where's Sean? And Chrissy? And KJ?
You missed a lot of people.
Yeah, I'm missing. Yeah, a lot.
KJ is coming.
Right. Sean?
Taxi.
By taxi?
Yeah, he slept.
Did he sleep over or oversleep?
He oversleep.
Okay. Alright, continue. So, Jerry, can I continue?
Yeah.
Okay. So, where's my, there we go. Right. So, here's an example. Actually, before I continue, have you talked about unstable atoms in chemistry?
Yeah.
You have? And what have you talked? Yes, they can lose electrons, yeah. They can lose other things too. They can lose electrons, yeah. An example of an unstable atom is the isotope uranium-239. Yeah? What?
I know.
What?
I know in 1947 about uranium.
Okay. This means it will decay. That is, alpha, beta, and gamma radiation will come out of it. So if you have your uranium-239, alpha, beta, and gamma will come out of it. Note, it won't do this forever. It won't continue to lose energy forever. Eventually, it will not do this. Now, we'll talk about that as well. That's for another class. So, uranium-239 is an example of something radioactive, but there's many other materials as well. So, there's three types of radiation. We said alpha, beta, and gamma. So, what exactly is each type? So, does anyone know what an alpha particle is? This alpha particle that comes off?
Proton.
Nearly.
Positive charge.
That is still true, but you're not 100% right. It's actually 2 protons and 2 neutrons. This is an alpha particle. Now, I deliberately didn't say about the electrons because there are no electrons on it. So if there's no electrons on it, what's the charge of an alpha? +2. Who's texting you? Don't be ridiculous.
What does that mean?
Interpret it whatever way you want. Not anybody in the class. No, okay. Right, did you get that? Yeah? Now, if you think about it, if an alpha is 2 protons and 2 neutrons, then actually what element is it if it's 2 protons? Helium. So in fact, an alpha, we can think about it as also a helium. It's identical to helium, except it doesn't have the electrons, so it's a positive charge. The symbol is alpha or He, because it's a helium. Don't worry, I found my cookies. They turned up.
Like, who would worry?
I don't know. When I got to my desk this morning, the 2 boxes were there. Okay, got that? Now the next one is beta, and actually Jerry already said what beta is, because you said in chemistry the electrons can sometimes come off. In fact, that's what beta radiation is. Continue? No. I see Jerry writing and Chu writing. What word are you on, Jerry? Okay. And Chu? Got it? Continue? Yeah. Okay. So, beta. Beta are high energy, that means high speed electrons. That's all a beta is. It just is a very fast moving electron. And the symbol for beta is beta, or does anyone know the symbol in chemistry? No, for an electron, come on. Yeah, but what numbers do you put on it? Very good, yeah, -1. Got that? Yeah? Okay. Continuing. The last one is gamma. Does anyone know what gamma is? Yeah, but what is it?
No, nothing.
Well, it's something.
Neutron.
No. Yeah, it's actually an electromagnetic wave, and the symbol is gamma. Okay. High energy here means high frequency. Very high frequency. Higher than X-ray or anything like that. We don't see them on Earth so much. You can see them in space, but not on Earth. Yeah. Continue? Yeah? Okay. So, next now. So, Newton's first law tells us that the atom should not just decay. Like, the atom just doesn't decay by itself as if by magic. Because Newton's first law says an object will remain at rest unless a rest or a constant speed, but let's forget about that part. It will remain at rest unless a force acts on it, yeah. So if the atom is just sitting here, and all of a sudden an alpha comes out or a beta comes out, well, it can't just do that. So, in other words, there must be some force that is pushing the alpha out and pushing the beta out and pushing the gamma to come out. There has to be some force doing that. And that force is a new force. We haven't learned about it yet, but it's called the weak nuclear force, and it's the force inside the nucleus that pushes the alpha, beta and gamma out. How is a good question, and it's extremely complicated. You're now into the area of quantum physics, which is well beyond this course. For us, it's enough to say that there's some force inside of it. And what's strange is it's only inside of a nucleus. So something happens when you put protons and neutrons together, where you get this force that appears. So what exactly is the weak nuclear force that does this wonderful decay? The weak nuclear force is a weak
nuclear force.
Yeah, part of me wanted to write that. It's a weak, well, firstly it's a repulsive force. So repulsive means it pushes out. And it acts only in the nucleus of an atom. That's the only place you see it. And not only that, the distance is very short. It only works for 10 to the minus 18 meters, which is tiny distance. It's the force responsible for nuclear decay. Now, I have seen in the exam, they have asked things like, give 3 properties of the weak nuclear force, 3 things about the weak nuclear force. So if you look at this definition, what are the 3 things you could say about the weak nuclear force? Well, the first one is easy, it's weak. Yeah. The second one is it's nuclear, meaning it's inside the nucleus. And you could say it's a repulsive force, or you could also say it's a short range force. So there's at least 3 things you can say about it. Okay, have you got that? Just open up my text file. Right. You might wonder if there's some counterbalancing force, which we'll have a look at later today, maybe. Because if you think about it, not all atoms decay. Okay, like if I have this here, it's not like there's alpha, beta, gamma coming out. It's only some materials decay. This one doesn't. So if there's a force pushing things out, then there must be something pulling it in that most of the time can balance and stop alpha, beta, gamma coming out. And we'll have a look at that later. So before we get on to that, just some terms, which I think you know all of these from chemistry. So the first one is the proton number Z. What are you shaking your head for? You don't know this one from chemistry?
What is this?
What?
You know,
Say
then
a-
atom together.
Yeah, what is this? What's proton number? Yeah, what is it?
No, hang on, don't mess with me. You know, you know proton number Z of an atom. What is it? Jerry, what's the proton number?
Proton number is the number of the
Oh,
mass.
it's the number of the protons.
Oh,
Yeah, the proton number Z of an atom is the number of protons in the atom. This defines what the atom is.
I'm right.
And you said number of electrons.
Oh.
No, it's not the same. It's not? No, it's not the same. It's not the same.
Of an atom.
The proton number Z of at atom? Oh my goodness, yeah, that should be of an atom. The proton number of an atom is the number of protons in the atom. This defines what the atom is. So if you have one proton, you have hydrogen. If you have two protons, you have helium. If you have three, you have lithium, and so on. Yep. So for the exam, this is enough for the exam. You don't need to write any more. For example, one proton makes the atom hydrogen. Two protons make the atom helium. And we can look up the atom, what the atom is from the periodic table. So the periodic table can tell us what the atom is. We know how many protons there are. You just need to write down the first two sentences, okay? So I just need you to write this down. So no. Continue. Right. The nucleon number. That's it. The nucleon number of an atom is the number of protons and neutrons in the atom. Note that normally the number of protons and number of neutrons are the same. Normally, I mean, not always. Yeah? Huh? Number of protons and number of neutrons? Well, that should be...
Protons and electrons around that are usually the same number, but protons and neutrons are mostly different.
Are they mostly... I shouldn't perhaps have said the same, but there should be similar amount, right? Like if you have something that has 20 protons, I kind of expect it to have about 20 neutrons, like around about that.
Yeah.
Is it not usually the same most of the time? See, I don't study chemistry. I thought they were usually the same. Or what is it? They're usually more or less? Much more? Like one more?
Yeah.
So, rather than saying normally that they're the same, I could say that they're similar, but then that's stupid, so I won't say anything. Right, continuing. The atoms of a chemical element can exist in different types. These are called isotopes. They have the same number of protons and electrons, but different number of neutrons. Different. Yeah, but not always. So like you could have one proton and no electrons,
Ah.
you know.
For atoms.
Not for, well, for atoms that have no charge.
Oh, yeah.
Yeah, but the atom could have a charge. It could have an electron missing or extra. So what's an isotope? An isotope has the same number of protons and electrons and a different number of neutrons, and different isotopes of the same elements have different masses. So an example is you can have hydrogen 1, hydrogen 2 and hydrogen 3. So in each of these, how many protons do we have? We have one proton, one proton, one proton. How many neutrons? No neutrons here, one neutron here and two neutrons here. So these are all isotopes of hydrogen. They're all hydrogen but with different number of neutrons. And since only the protons make it what it is, it's still a hydrogen even if it has more neutrons. But you know what isotopes are from chemistry. And Jerry, you know isotopes and what's ions? Oh, yeah, I think you know ions. Don't you know ions? Yeah, if you have extra electrons or missing electrons.
Ion.
That's what I said, ions. Continue? Yeah? Okay. It's okay? Hydrogen 1, hydrogen 2, hydrogen 3 are all atoms of hydrogen. However, H2 and H3 are isotopes since they have more than the usual one neutron. And remember, hydrogen has one proton, so that's why they're all hydrogen. The extra neutrons make the hydrogen heavier. So this is heavier than this, and this one is heavier than this one. Right, so back to our alpha, beta and gamma now. Alpha, beta and gamma, they have different penetrating power, meaning some of them are harder to stop than others. Alpha is very easy to stop. In fact, your hand can stop an alpha. Beta is a little bit harder to stop. You would need some metal, aluminium maybe, and that can stop a beta. Gamma is the most difficult to stop. You would need a big piece of lead, TB, lead, to stop it. Yeah. Or maybe something like 1 meter of concrete, of stone, to stop gamma. Okay, so gamma is very difficult to stop. Each of them are also harmful to you. So interestingly, the most harmful one is the one that's easiest to stop. And the least harmful one is the one which is hardest to stop. Which is good. Huh?
But can it penetrate to the...
Alpha has the highest ionization power.
Yeah, most energy. But it's also the one that's easiest to block. In fact, your clothes should be enough to block alpha. Alpha is only harmful if it gets inside of you. So if you drink something or you cut yourself or something like this, the alpha radiation can't get inside of you. But your skin and your clothes could stop it. Beta is a little bit harder. Beta will penetrate your skin, so it's more damaging then. Yeah?
Lead is nice.
Lead?
Yeah, it can protect you from the waste of
Yeah, the lead is used to protect people from nuclear waste.
Yeah, a lead box.
Lead box, yeah. But you need like a good piece of lead. It needs to be thick. Yeah. Continue? Yeah. What I would need you to write down, you could draw this or you could just describe it in words. So your hand would block alpha, a piece of aluminium would block beta, and a big piece of lead would block gamma. So you can write this or you can draw this, whichever you prefer.
X-ray could be the gamma.
Say again? X-ray is the frequency before gamma.
So it's
No, beta is a different thing. Beta is an electron, gamma is a wave. Yeah. If you wanted to think about X-ray, I would put an X-ray kind of in between the two here, in terms of how much it can penetrate. Because obviously an X-ray will pass through your hand, but not quite through metal. So it would be comparable to a beta. Continue. Are you drawing this?
yeah.
That taxi's taking a long time.
Taxi is so expensive.
Yeah, well, it's a taxi, not a bus.
Unless you're with Chrissy. It's a thin part.
Oh, Chrissy. Buy emoji.
It takes like 10 something from city center to here.
That's alright.
I mean, it's so near.
Yeah. But I mean, if it was raining. Where in the city centre?
Huh?
Where in the city centre?
The W1. But it's like, I don't know, like 16 something.
Okay. Well, she shouldn't take the taxi much if she lives on campus, right?
But I move.
Who moves?
I mean, no, I don't mean move, I mean I go out.
Oh yeah, okay. Continue? Yeah. Let's look at more details here. So you saw me using this symbol earlier. Is this the same one you use in chemistry? Yeah. Sorry if I'm boring you. This bottom number is the proton number, and this upper number is the nucleon number. Yeah, and this X is the element, yeah. Okay, you can write that down, please. So this is the element, the proton, and the nucleon number. But you know this from chemistry, so that's fine. I know. I told you at the start some of this you will know already. Okay, continue. Yeah. Right. During radioactive decay, there's 4 quantities which are conserved. So, let's say, it's not working right now, but I don't really need it. So you have your uranium, and off it comes an alpha, off comes a beta, off comes a gamma. The whole process, there are 4 things which are conserved. So they are, the first one is energy, conservation of energy, of course. So the energy you have before the decay will equal the energy after the decay. Of course you don't lose energy, but we know this one. This is a basic rule of physics. So the first thing you can write down is that energy is conserved. Do you understand, Jerry?
Yes.
Are you sure? I said 4 things are conserved. What else do you think might be conserved? So, after the decay process... Huh?
Momentum.
Correct.
Really?
Yeah. So at the beginning the momentum is 0. M1U1 plus M2U2 is 0. Then afterwards the M1V1 plus M2V2 should still be 0. So that means, of course, if the alpha moves out this way, then the remaining atom will recoil backwards. So, momentum is conserved. What else?
Wait. The body.
Charge. So, if this guy loses a +2, then what happens to this guy? If this one's a +2, then this, -2. So, if this one has a charge of +2, this one loses then 2. So this one would be like this one has 2 extra electrons if the alpha leaves with a 2. So charge is conserved and momentum is conserved. So momentum and charge. But what's the last one? What the heck is state? What? Conservation of state. If it's a solid to begin with, it will be a solid at the end. No.
How about the gravity?
No, actually.
I'm all.
No. Believe it or not, mass is not conserved. Yeah. So the last thing that's conserved actually is it's the nucleon number. The number of protons and neutrons in total is constant.
But alpha particles consist of 2 neutrons.
There's 2 protons and 2 neutrons. That means there are now 2 protons and 2 neutrons less in the material.
Yeah. It's changing the Nucleon number.
Even though for the total, like so at the beginning you have all your protons and neutrons, and afterwards when they separate, the number of protons and neutrons here plus the number of protons and neutrons here.
That is not conserved. I give out my food and it is still mine because it is.
But it is conserved because it's like with the momentum. This one has no momentum at the beginning, okay, and then afterwards this one moves back. Is his momentum conserved? Well, it's changed, but if you add it to this momentum, you still get 0.
Okay.
No, but for the charge, you were all happy with the charge and the momentum. So if this one carries off a 2, this one loses 2, and nobody was saying, "Teacher, this one loses 2, it's not conserved." Why are we saying this for the nucleon number? I'm not sure.
Because it is easier to imagine for nucleon number, but it's hard to charge. So
right, okay.
You know that, we're just like, okay.
Fair enough. When we talk about something conserved, we mean for the whole system, not for an item in the system. This might seem obvious, but Jerry suggested something which might seem obvious too, that the mass should be conserved. So for example, if this is 1 kilogram and then 1 gram exits, then afterwards you should have 1 gram plus 999 grams, and believe it or not, you do not in the decay process. That there is something strange happening with the mass, which we'll talk about later. It's later in the chapter. So these are the 4 things you need to note that are conserved. Do you have them?
No.
Yep, okay. So, some simple reaction statements. Since alpha has 2 protons and 2 neutrons, then when it decays, the number of protons and neutrons decrease by 2. This makes perfect sense if you think about it. Like, if you have something here, and an alpha particle leaves it, then the number of protons reduces by 2. And the number of neutrons inside here reduced by 2, because the alpha particle, which is 2 protons and 2 neutrons, has left. So that obviously makes perfect sense. Okay. So the next statement, since beta is 1 electron, then the material decaying will see the number of electrons decrease by 1. Well, that makes sense, doesn't it? If a beta comes out here and it has 1 electron, yeah, it has 1 electron, what happens to the number of electrons here? It reduces by 1, because 1 has left. Again, that makes sense, doesn't it? However, something funky happens now with beta. So not only does one electron leave? Okay, get ready for this now. This will blow your mind. One neutron will turn into one proton inside the material. Yeah, that's the look I was looking for. When the beta leaves, one of the protons that was inside the material will turn into a neutron. Sorry, did I say that backwards? Sorry, yeah. Oh, well, that makes much more sense. One neutron will turn into one proton. Which is very strange. You might say, why would an electron, when it leaves, cause a neutron to turn into a proton? No, it's not quite. Now you see, there's something very funky, like I said, happening inside of it. But this is beyond. The reason why is beyond this course, because again, it's quantum physics, advanced stuff like this. But it's enough for me to say, and for you to know, that when the beta is released, somehow a neutron will convert into a proton.
When something will come into the nucleus.
Another force?
Yeah.
Well, it's very complicated. There's no easy answer I can give. It's just observed that it appears a neutron becomes a proton in this process. That indeed is very odd. One neutron will become one proton. Now, think about this. We said the number of protons tells us what the material is. So if we lose a proton, that atom has changed. No, but here, lose an electron. If one of the neutrons turns into a proton, then this atom has changed.
Yeah.
It's the next atom on the periodic table. So when a material is decaying and it's releasing beta radiation, it is slowly changing into another material over time. No, not for the alpha, just for the beta radiation. Yeah, but it's losing it, it's decreasing it. Yeah, I guess what I was thinking about in my head was with the beta, you're not really losing mass because you're just losing an electron. So the material is slowly changing. Whereas with alpha, as you're losing protons, the mass is shrinking, but it's also changing because you're losing protons. Now what's interesting is both these processes are happening usually at the same time. So you usually have an alpha and a beta. So you might say, how did the two work together? The alpha makes it want to lose two protons, and the beta wants to gain a proton, one proton from one neutron. So depending on the relationship between the alpha and the beta will affect what it looks like as it decays. Yeah?
So for one alpha is even two beta. Then it will be two
if you had one alpha and two beta, then it kind of looks a bit more, the material is a bit, it doesn't look like it's changing. It'll still lose mass though. Because at the end of the day, alphas and protons and neutrons are still leaving. Anyways, the last one is gamma. Yeah, that's weird, but it happens. Gamma has no particles, so nothing changes in this regard, although some energy is lost from the material. Well, if the gamma energy releases, then inside the material some energy is lost. So the total can be the same.
Yeah, what's the meaning of oddly?
Oddly, strangely. If you wanted to understand this more, you would need to take a course in nuclear physics. There's not going to be any easy answer to why it does these things. Continue? Yeah?
So this gamma has no particles?
Yeah, it's a wave, electromagnetic wave. Yeah.
I was wondering how they can detect gamma.
Yeah, we will actually look in another lesson. We'll look at the device we can use to detect alpha, beta and gamma. Gamma, I suppose, think about it, you could detect gamma the same way you could detect X-rays. Yeah. But there's other things you can do, like gamma has a high energy. So you would know if you have gamma, if you have some gas that maybe becomes ionized by the gamma energy. But I think you could detect it by using the way they detect the X-rays, using the photoplate, I think. Continue? Yeah? When a material decays, we can represent this as an equation like you've seen in chemistry. Okay. And I think we'll actually have a look at that in a little bit. Let's have a look at an example here. So, I'll explain. You can use your chemistry equations here. So, a small amount of uranium-239, which is 0.01 nanograms, is decaying. Represent this decay as a nuclear equation. Alright, so how do we write uranium-239? Rats, what is the number of protons in uranium? I don't have a periodic table. Do you have one?
Oh, I didn't do chemistry, so...
No, come on. Chemistry, study. We do not have any chemistry.
What? What are you asking me?
How many chapters are we in?
92.
I don't know. 92, thank you. So, this uranium, if it's an alpha. Who's this now? KJ, come on in.
What?
You took a taxi and a skateboard?
I didn't.
You didn't take the taxi. He lied to you. What was it saying? What was that? So the uranium, if it's undergoing alpha, okay, if it's undergoing alpha, you have something which is not uranium. KJ! Oh, KJ. So messy.
Nice sweater, teacher.
Yeah, yes. No, you're lucky this didn't land on my new sweater.
And computer.
And the computer, yes. Oh, KJ. Huh? Don't worry about that. It's leather, so it'll be fine.
No.
Yeah. This looks okay.
It's wrong.
Oh, dude, out of tissue. We'll leave it. We'll get some later. Wait, actually, Lee, aren't you in this building? Aren't you?
What?
You have tissue in your apartment, I assume.
Apartment, yeah, of course I have tissue in my room. You want me to go down?
In a little bit. No, actually, no.
I have here actually.
What the heck is that?
I don't know.
Everybody has weird packs of tissue.
What is this? I think it's from September, right? Yeah.
Right. Now we're talking.
Oh, the positive one is you can have coffee smell.
Yes, indeed. Right. Thank you. Okay, we shall continue. Right, so the alpha, how many protons is lost? 2. So this 92 becomes the 90. And how many nucleons are lost? 4. So this becomes a 2, 3, 5. And this is plus your alpha here, which is 4, 2. This is an example of an alpha decay. By the way, what is the element? It's whatever has 90 protons. Do you mind checking that for me, Monica? So what has 90 protons?
Uranium.
Now uranium has 92. TH. Okay, the next one is beta we'll look at. So what happens with a beta decay? Yeah, so it loses an electron, so there's an electron out here. Now, if the uranium underwent a beta, remember what I said, 1 neutron becomes 1 proton. So the nucleon number does not change. Because if you swap a neutron and a proton, the total is still the same. But what does change? This is a... Well, I'm just starting again from this one. Oh, 239, sorry, thank you. 239. And this one is 91 for this example. No, sorry. 93. And again, Monica, since you have your phone handy, what is number 93? NP. And the last one is, what would gamma look like?
Nothing.
No, not nothing, but rather it's still uranium
Plus energy.
plus this gamma. We could write 0, 0 here if you wanted. Now this is a lot like what you do in chemistry, isn't it? It's your reaction equations.
We do this.
What? Have you done your reaction equations? Yeah. Now notice that this number equals this number plus this number. This number equals this number plus this number. This number equals this number plus this number. Likewise, this number is this one plus this one. 92 is 93 plus minus 1. 92 is 92 plus 0. Okay, so that's part 1. Now part 2. What is the velocity when an alpha particle is released at a speed of 0.05? So you have here uranium-239. And then what happens is your uranium-239, an alpha particle fired out here. So what will happen to this? It will jump back. Conservation of momentum. What's the momentum beforehand? M1U1 plus M2U2, 0. And here this is M1V1 plus M2V2. This is V1 and this is V2. So V1 is minus minus M2 over M1 V2. Is that all right? Yeah. Now, do we know the M2? Well, actually, let me just draw that in. This is the M1, and this is the M2. 1 alpha is released from this piece of uranium, so it's 0.01 nanograms. So we know the M1. Do we know the V2? We do. And do we know the M2? I haven't told you this. It's the mass of a helium, which I haven't told you, but we can estimate it roughly. Calculator. Okay. Move back. Yeah. Open the calculator. Where's my calculator? There we go. Okay, so on the top we have M2, and on the bottom we have M1, which is 0.01 nanograms. And then we have times V2, which is 0.05 times 3 times 10 to the 8, isn't it? And then on the top we have the mass of the alpha. Now I never told you what that is, but what is an alpha? Yeah, which is made of what? 2 protons and 2 neutrons. So we can roughly say it's 2 protons plus 2 neutrons. Now, yeah, believe it or not, it's not exactly this, it's just roughly this. What constant is a proton here? It's 1, and a neutron is 2. So you get this tiny little recoil. 10 micrometers per second. So when the alpha particle comes out, this one moves back a little bit slowly. Yeah. Part 3. In part 3, I want you to do the same thing except when it's a beta. So when you think about it, what's the only difference if it's a beta in my formula? The mass. It's only the mass that's different. So in my calculator, the only thing I need to change is what? This top line. Because everything else is the same. So what is it? That number 3? Mass of an electron? Now this should be tiny. It is 10 to the minus 9. So that is 1.37 nano. So in part 2, you will get minus 1.37 nanometers per second. Now, that makes sense because electrons are about 1,000 times smaller than protons and neutrons, so this does make sense. Next one. How much energy does the alpha have? Okay, well, what is the energy of the alpha? What form of energy will it have, yeah? That's it, a half mv squared, which is roughly, we don't know the mass of an alpha, but we think its mass is roughly 2 protons plus 2 neutrons. Wow. What happened to you? Studying physics last night?
And I asked him to, when you do break, tell me.
Oh, I haven't taken a break yet. Continuing. Okay. Now, as I was saying, the mass is not exactly 2 protons and 2 neutrons, it's roughly 2 protons and 2 neutrons. So do we know the mass? Yeah, roughly. Do we know the velocity? Yeah, 0.05 c squared. Let's put this in on the calculator. A half mass of the proton plus mass of the neutron (0.05 times 3 times 10 to the power of 8 squared). Now, because this is a small amount of energy, what's a good unit to use for small energies?
EV.
Electron volts. So I'll divide this by 23, isn't it? And that's how many zeros? 1, 2, 3, 4, 5, 6. So that's mega. So that's roughly 4.7 mega electron volts of energy. Okay, the last one now. Is this 5? 1, 2, 3, 4. How much energy does the beta have? Well, what type of energy does the beta have? It's kinetic, except what's the difference here? The mass is much smaller, isn't it? Again, we'll use electron volts. (640 electron volts). Yeah. Got that? Continue? So can you see that the alpha has much more energy than the beta at the same speeds? Yeah. Next now. So, how many alpha and betas are emitted when that decays into that? So, you have uranium, yeah, very good. Uranium-235, 92, that becomes lead, 207, 82 ppb. Because some alphas and some betas were released. But we don't know how many alphas and betas, and we want to know how many alphas and betas. So, as Jerry suggested, we'll say there were X alphas plus Y betas. And our question is, how many alphas and how many betas? So, Jerry, since you had the idea, maybe you know what to do next for this one. Thank you, Captain Obvious. And then after finding X, what could we find next?
Subtract and then divide by 4.
Find Y, I think. Oh, sorry, what? Yeah, I know, but I want something nice.
Plus 207 equals 235.
Yeah. I kind of want you to see that you can say 235 should equal 207 plus 4x. Because that's the total there, plus 0 y's. And you can also say 92 should equal 82 plus 2x minus y. Now, if you look at this one, 235 minus 207, that's that 8, isn't it? 28 is equal to 4x. So x is 7. And if I put that in there, I get 10, 4, yeah. So, when uranium turned into lead, it produced 7 alphas and 4 betas. And there's always some gamma, but we don't actually know how much that is. Is this similar to how you balance equations in chemistry? Only kind of similar. Yeah. What is it that you say is equal on the left and the right when you're balancing an equation? Huh?
We do the PB2 plus and PB3.
Yeah, like what is it? What is the thing that you say is equal on the left and the right? The number of moles of what? So, in other words, you have the same amount of atoms on the left and the right. Yeah, so like give me an example of a reaction you do in chemistry. Because 2mg O here. But the question might be, find this number. Like what would you be asked to find? Yeah, so like what would be missing? Yeah, like a number here. And this too. Yeah, okay. Oh, in other words, find the coefficients. Oh, I see, okay. So you would have to say whatever this number is, it has to be the same as this because the mg, yeah, that should be a capital M, shouldn't it? I get you. So if this is an x, then this has to be an x. They have to be the same number. And then here this is an O, but this is an O2. So if this is a Y, this half of this has to match that. Yeah, I see, okay. So you would have to pick a number here that you can, so this would have to be an even number, so you have to half it. And half of it has to be the same as x, so something like 1, 2. Did I do that right? 1, 2, 1? I should have started with the O. Yeah, so this number here has to be a 2. Now what am I saying? This has to be a 1 and this has to be a 2. So this makes your 2 oxygen. But then this number has to be the same as this. That has to be a 2. So 2, 1, 2 then. Okay. So you're not really forming equations. Okay, but it's usually like this then. But I'm curious, just from a maths point of view, can we form equations? Like if I said xmg plus YO2 equals ZMGO, what equations can we make here? So I know that x must equal z. That's one equation. I need 3 equations. I know that y 2 is
do that.
2y equal O. 2y equal Z.
Y equal to O. 2z.
no.
2y.
No, 2z.
2z.
What?
Y equal to z.
What?
Because O2.
Yeah, O.
Isn't it? The number of the O's is the same. Oh yeah, sorry. We're all doubting Jerry. 2y equals z.
What? Why? I don't get it.
Yeah, no, that is it. Yeah, yeah. Because you have, how many oxygens do you have here? 2. Y. If this was a 1, how many oxygens do you have? 2. Yeah.
Y is 4 oxygen.
Yeah. So that means if this is a 1, what does the Z need to be?
2.
It has to be 2. So 2 times 1 equals 2. No, Jerry was right.
Yeah, Jerry was right.
Yeah, we should believe Jerry. Now, if we wanted to solve this mathematically, we still need to make one more equation.
Y equals X.
2y equals x.
2y equals X.
What? No.
Because
We only can make two.
But it's the same thing in just two equations. It's the same thing.
Yeah, you see, I think with these chemistry ones,
the chemistry.
you can't make 3 equations.
You can't.
You can't because, in fact, there's multiple answers. Because I could have said 2, 1, 2 is an answer, but I also could have said 4, 2, 4 is an answer. So what we have to do is, you have to choose a value for one of them, x, y, or z. So in this last one here, we just chose to make the y 1.
But 2 questions we can add it. We can add like
From these 2?
Yeah.
No, you can't.
We can't. I mean, we can't get the real number, but we can get the relationship.
Yes, that's what I'm saying. I want to know, can we get the real number? And the answer is no, unless we choose one of these. So for example, if I said y is 1, then x and z are both 2. Yeah. So for the chemistry, we can't, but for the physics and the nuclear equations, we can. That is what I wanted to have a look at. Okay, so these are very important for the exam for 2 reasons. They're quite common and they're quite easy. They're just linear equations. The reason I like the atom question in the exam is because you get nice questions like this. So for example, the first one, you need to use your periodic table for this one. Yeah.
Do you have new chemistry teacher?
Haven't a clue. Nobody tells me anything.
I was told that there's a young and sweet teacher.
Who told you this firstly?
I don't know, from another class.
I see.
Really?
Would it be sweet?
Yeah, but I'm not sure if she is the one.
She or man?
Is it she?
No, you see, this doesn't make sense because you can't know more things than I do, because then that would mean people are telling the students things before they tell me things.
Yeah, maybe that's true.
Who told you this? Who's your source?
My roommate.
Who's your roommate?
From science class. I'm not sure what class he is in.
Camila said yesterday she is going to have interview today.
Yeah, so...
yeah, maybe she's the one. The young and sick teacher.
Oh my god.
But if there's only going to be an interview today,
Yeah.
And she was chosen.
like, you don't know. Like,
we are going to vote.
but hang on, you can't choose someone before the interview. That's not how it works. No, I think your roommate has inaccurate information. I'm sorry to say this. Who is your roommate?
You do not see?
Yeah, hang on, don't doubt what I know. Who is it?
Waiting.
I don't know.
So actually she's the one because we have class tomorrow. And then Corona said we have a class tomorrow.
Really?
I mean, we have to.
She said
We are
we do
going to
not
start
have to
topic
take
yesterday.
Interesting. What'll happen is I'll find out tomorrow when somebody asks me to make a new email account for the new teacher. That's how I'll find out. Okay, can you take a picture of these and try these now? For number 1, you need your periodic table because there's an element missing here. And in number 3, it's like the example I did. I want to know how many alpha and betas are here. So this is like my example. This one here, you need your periodic table. So for example, in the first one, well actually you don't need the periodic table for the first one because what do you have here? Uranium 239, 92. Here you don't need the periodic table. Here you do need the periodic table because this element will have how many protons? 11. So I don't know what has 11 protons. Do you understand? Yeah? Is it sodium? Cool. Can you try these?
I love this.
Go for it.
M is nucleon.
Oh, yeah, I'm sorry, I didn't write that down. Did you see this before? N stands for a neutron. Well, even if you didn't know that, if you look here, it's the thing with no protons and one neutron.
Yeah. And then there's gamma on the other side.
Gamma is like 0, 0. I can't stop saying gamma is nothing, because, you know, it gives the Hulk its superpowers. So, it's something, for sure. It's 0, 0.
So it may have very much for them.
For balancing the equation, yes. Yeah, because we still haven't talked about the funky thing that's happening with the mass. Can you do these, Andrew? Like your phone. Your phone. Your phone.
Did he answer you? Haven't.
What? Huh? Okay. Back to maths. Well, right now it's more like maths and physics. To what, Jerry? Oh, I should actually stop the video so I don't need to